Today we shall talk about the basics of ocular alignment. It is common knowledge that both eyes work together in coordination, and when they don't, just the facial appearance tells that something is amiss. Even a lay person can notice it. Let us add a scientific perspective to it. What is normal ocular alignment? When I ask this question to undergraduates or even postgraduates, the answer is often not coming forth readily. Usual answers that I get is that the normal alignment is when the eyes are straight or when the eyes are parallel. Though both these answers appear to be correct, they are scientifically not accurate. So let us see what is normal ocular alignment. Normal ocular alignment or coordination is when both the eyes are directed towards a common object of regard. See here, the fovea of the right eye and the fovea of the left eye, they are directed towards a common object of regard. And this happens in all directions of gaze and for all distances. That means near distance, dextroversion, levoversion, elevation as well as depression. So this is normal ocular alignment. What ensures the ocular alignment and maintains ocular coordination? The desire of the sensory system to enjoy benefits of binocular vision drives the motor system comprising of the extraocular muscles to keep the eyes aligned and remain directed to a common object of regard simultaneously. The aligned eyes in turn reinforce binocular vision. Thus we see that ocular alignment and binocular vision enjoy a mutually reinforcing relationship. We also see that the motor system is at the service of the sensory system. The prerequisites for binocular vision are good and almost equal vision in both eyes, aligned eyes, intact visual pathways, intact fusion center in the cortex. When both eyes have equal or almost equal vision and are aligned, then an object of interest generates a stimulus for image of equal size, luminance, color and contrast at fovea of both the eyes. Visual impulses are transmitted by visual pathways to corresponding areas in the visual cortex. As each retinal area or unit is part of the retinocerebral apparatus, images of same size, illuminance, color and contrast are perceived by the corresponding areas of the cortex. These two similar images are fused and perceived as one. Fusion has a range and promotes depth perception. The fused single image is localized in a direction specific to the stimulated retinal area, which is in relation to the straight ahead localization of the fovea. Let me explain this further. So if a object of regard stimulates the fovea, it is localized in a straight ahead direction. Whereas if the object stimulates the retina on the right side of the fovea, it is localized towards the left side, and when it stimulates the retinal area on left side of the fovea, that means nasal side in the right eye and temporal side on the right eye, nasal side in the right eye and temporal side in the left eye, then it is localized on the right side. Binocular vision has grades or components. Grade 1 is simultaneous macular perception, that means ability of both the macula to perceive simultaneously. Grade 2 is fusion, that is ability to fuse the images seen by the two eyes, and fusion may be weak when it has no or little range, or it may be strong when it has a larger range. third or the finest grade of binocular vision is stereopsis or depth perception. In order to enjoy the binocular functions, the eyes must remain directed towards the common object of regard at all times. And here comes the role of the extraocular muscles. The six extraocular muscles, along with the orbital fat, tenons fascia and pulleys, support the eyeballs, keep them aligned, and enable coordinated ocular movements. These are illustrated here in figure 3a, this is the lateral view, and figure 3b, this is the anterior view. See, the four recti, lateral, medial, superior, inferior, and the superior oblique, take origin from the zonule of Zinn at the apex of the orbit. So they take origin somewhere here at the apex of the orbit. And the inferior oblique takes origin in the anteromedial part of the orbit near the lacrimal grooves. So it takes origin somewhere here. So we can see the medial rectus, inferior rectus, lateral rectus, superior oblique, and the inferior oblique. Third cranial nerve supplies all the extraocular muscles except the superior oblique and lateral rectus, which are supplied by fourth and sixth cranial nerves respectively. The tenons fascia covers the eyeball. You can see it here. And it ends anteriorly at the limbus. It envelops the extraocular muscles as a sheath as they pass through the tenons to reach their insertion on the eyeball. The facial connections are illustrated in figures 5a and b. You may pause for a little while to read this text or proceed directly to the illustrations. The facial connections and pulleys are illustrated here. This is the anteroposterior view of a coronal section, and this is the lateral view of a sagittal section. The extraocular muscles are connected to each other by condensations of connective tissue called the intermuscular septum, which together forms a conical ring. You can see this here. You can also see this here. And this divides the orbit into an extraconal space and an intraconal space. The oblique muscles have connections to the adjacent recti muscle. The superior oblique has connections with the superior rectus muscle, and inferior oblique has facial connections with the inferior rectus and lateral rectus, which together forms a hammock called the Lockwood's ligament. It provides support to the orbit, and it also has connections to the inferior lid retractors, which allows coordinated movements of the lid in down gaze. In addition, there are connective tissue condensations which attach the muscle sheath to the orbit. You can see this here, you can see this here, you can also see this here and here. These are called the pulleys. They stabilize the muscles and also have an effect on their actions. The medial rectus muscle has a straight course and does not have facial connections with adjoining oblique muscles. During surgery, therefore, this is vulnerable to get lost and is difficult to retrieve. The ocular movements are versions and versions. Versions are when eyeballs look towards the same side. So when both the eyeballs look towards the right, this is dextroversion. When they look towards right and up, this is dextroelevation. Right and down, this is dextrodepression. Similarly, there is levoversion while looking to the left, levoelevation and levodepression. In addition, there can be direct straight ahead elevation and direct depression. The muscles of the two eyes that act together, that means in dextroversion, the lateral rectus of the right eye and medial rectus of the left eye, they are called the yoke muscles. Similarly, in levoelevation, the superior rectus of the left eye and inferior oblique of the right eye are the yoke muscles. The vergences are disjunctive movements where the eyeballs either move towards each other, that is convergence, or away from each other, that is divergence. And the convergence and divergence are used to adjust for an object which comes close or away from the observer. In this figure, you can also see the nerve supply of the muscles, the third nerve, the sixth nerve, and the fourth nerve, as I have discussed earlier. The movements just described are coordinated, and the fundamental laws that ensure this are illustrated in figure 7. You may pause to read this text or skip and go straight to the illustrations. The Herring's law is of equal innervation. It says that the yoke muscles which act together receive equal innervation. For example, in this picture, this is showing the eyeballs in dextroversion. The yoke muscles acting here are the right lateral rectus and the left medial rectus. They simultaneously receive equal innervation or energy of 4 plus. Right? And the Sherrington's law is law of reciprocal innervation. It says that when a muscle is contracting, its agonist receives lesser innervation so that it can relax to allow a smooth movement. Now in this figure you can see that while the right lateral rectus is contracting and receiving 4 plus innervation, the right medial rectus, which is the antagonist muscle, is receiving only 1 plus innervation and it is relaxing. Similarly, while the left medial rectus is acting and receiving 4 plus energy, the left lateral rectus is simultaneously relaxing and receiving only 1 plus energy. Thus we see that maintaining ocular alignment is not a static but a dynamic process that requires very high degree of neuromuscular coordination between several factors such as the fusional reflexes which guide the other reflexes, then accommodation and ocular movements. The refractive status has a role in the accommodation and accommodative effort, and extraocular muscles control the ocular movements, which are versions and vergence. The convergence is a much stronger active process. It is represented by this thick and large arrow, whereas divergence is a less strong and a passive process, and this is represented by the thinner arrow. So with the interplay of these factors, the eyes ideally should remain in a straight position, which is called orthophoria, which means that there is no deviation even under cover. But being a dynamic phenomenon, smaller deviations from this ortho position are also considered as normal, and the normal ocular alignment has a range which is orthophoria. Esophoria up to 6 prism diopters, exophoria up to 10 prism diopters, and small vertical deviations up to 4 prism diopters. We see here small degrees of ESO deviation and larger degrees of exo deviation can be controlled because convergence is a stronger phenomenon. That is why larger degrees of exo deviation can be controlled. And the oval these diagrams that suggest that even smaller degrees of the degree to control vertical deviations is smaller. So we notice that larger degrees of horizontal deviations and very small degrees of vertical deviations can be controlled. So when the deviation can be controlled, that means either there is no deviation under cover or there is a small deviation under cover, but as soon as the cover is removed, it is controlled. This is called phoria, and all these phorias, they come in the normal range. But when the deviation appears under cover and does not disappear and after the cover is removed, it is called intermittent tropia or intermittent squint. And when it is present all the time, it is called tropia or constant squint. Inability to maintain ocular alignment results in squint or strabismus. Squint can be defined as inability to direct the eyes simultaneously at a common object of regard at all times, sometimes, or in certain gazes. Squint therefore may be latent or phoria when it appears only under cover. Intermittent or intermittent tropia when it appears under cover but does not disappear when cover is removed. Intermittent breakdown may be only for certain distances or gazes. And constant squint or constant tropia which is present all the time. We will discuss squint in detail in subsequent sessions. Let us now revise and also test our understanding with the help of MCQs. You can go ahead to attempt these MCQs. The key is given at the end.